In this lecture, we're going to have a discussion on source potentials. Source potentials are very important because they help us to approximate the lift on a wing. The concept seems to be abstract and how that really works, but understanding how the source potentials work, we will going to extrapolate that to approximate the lift and the drag on a flat wing, let's say. Okay, so to understand this, let's fix some ideas and concepts together here. The first thing we want to fix here is uh, when we talk about a fluid source or a potential force, we say potential because it's possible to have a potential. You can think that at a point, somehow there's a flow that's coming out or is going in, okay? So it can happen in any direction. So it's actually a three-dimensional problem. And we can approximate, many times we approximate that in 2Ds, but we will start with a three-dimensional model and we will simplify that to your three-dimensional one. Three-dimensional to a two-dimensional one. So note that we always call the mass flow M, right? So now is a common practice in aerospace, in aerodynamics, and among the aerodynamicists. When we talk about source flows, instead of using M, we like to use Q. Do not confuse Q with a heat sink. This is a flow sink, okay? So the mass flow rate, then, as you know, is going to be mass over time. And this will be rho times Q, where Q is the volumetric flow. So in other words, this will be dot, okay? And this is given by the following equation that you have here, okay? In other words, if you want to really understand what that is doing, if you just remember, this is nothing else. The volumetric flow will be nothing else. I like to call it dot. We call it here Q. Okay, I'm sorry, this is Q bar here. And this would be your velocity I, and I times your area I. Okay, we already worked with this before, equations similar to this. Okay, so this is over a sphere. So now that we have this, and we actually kind of derived this previously, but let's go ahead and do that again. So for a flow in a straight line, so it goes directly from the middle and it's going in straight lines. Okay, so it's going outwards, doing like this. It's going out, equal, and all of these are identical. It's uniform. Okay, so this is going to equal to UR ER. Okay, let's use capital R. And then your N would be nothing else than ER. And your total vector R will be nothing else than RER. Okay? So now we know that your Q, your volumetric rate, is UR, that's a function of R, big R, will be 4 times pi R squared. Remember what I told you, right? This is nothing else than the velocity times your N I times your delta S. This is over the surface, okay? This is over the surface of the sphere. Okay, and this is going to be a value that's constant. That's going to be the same. So You can further, if I go ahead and do this, I know my potential is going to go to partial of the capital R, and this is defined as my Q divided by 4 pi R squared. So from here, if I compare this and I integrate both sides, then you can show that your potential flow then would be source potential would be nothing else than Q over 4 pi R plus a constant. Okay, so this is what your source potential will look like. If you want to know what your stream potential will look like, then you can do the same thing. Just know that this is equal to R squared sine of theta, partial of theta. This is going to equal to Q 4 pi R squared. And then from here, you can show that what you have is this is equal to theta. This is Q over 4 pi sine of theta. So this is going to equal to this. So from this, you can see that your psi, your stream, source stream would be 4 pi. If I integrate on both sides, gives you sine of theta. This is cosine of theta plus a constant. Okay, so this is how I will find my streams as we have been doing before, right? So let's move on. So in cylindrical coordinates, your sines and cosines expressed by the following equation right here, where this is your r, this is total distance r, then this will be total distance x, this is theta, your angle theta here, and again, if you can realize that I'm using x in this direction and I'm doing in z, that's why I'm using theta instead of phi. We interchange this all the time. And then r is equal to y squared. Your small r here will be, you can take this is z, and this is y. So it's y squared, z squared, the square root of that will give you r. Okay? So that means using then our relationships, you can see that I have sine here, right? Cosine is equal to this. So I replace cosine there. And then, so by that, you can show that your expression, this is your big R. This is your big R. So expressions are equal to this. And it's important to know that the strength of the sink is minus Q and the source would be plus Q. So sink, if this is the point, is sinking, right? You can think like when you are in the sink and you spill water and that's going inside, that's going all the way inside. Okay, so this is sinking. Your source is something that's generating the flow, is going outside the point. Okay, so that's why this will be plus Q, this will be minus Q because it's going actually inwards instead of outward. Okay, so let's understand now how does all this stuff really work. To understand this, let's consider this case. This case, the source on a uniform stream. Let's consider Rankine shape. This is nothing else than a shape as you see here. So think about a cylinder that's semi-infinite. Why is infinite in this direction? Is infinite in this direction, but finite in this. And this is a stagnation point. As you know, the stagnation point is a location where your velocity is going to be zero when it touches here. Okay, so you know that your velocity here in your stream will be zero. And then this is a source. You have a source of flow that's coming here, and it's going, the flow is going in this direction, going in this direction, it's going on all these directions, right? Because the source is flowing. Okay, it's kind of uniform right here. It's a perfect sphere, but then as you go in far field, it does something like this. Okay, so what we want to do is we want to study this type of problem, and we want to see what the potentials are and how do we study that. So to do that, let's go to part A. The potential velocity would be nothing else than potential is equal to 0, okay? And the gradient of this will be the source. And then just remember that we also have the flow. Okay, so now what's happening here is not only the potential of the flow, but I also have a potential of this source that's going to affect my problem. That's also, so that is flow, or let's call it, this is flow. And just for clarity, this is uniform. It's a uniform flow, and that's equal to 0. Okay, so if you remember, we said that if I did this, this is possible to add both. This is 0, right? 0 plus 0 is 0. So I can add both of these. So this is source plus flow is going to be 0. 0 plus 0 is 0. That's fine. We can do that. So if that was the case, then this is the same as, this is your total potential would be the source plus what happens to the flow, to the potential of the flow. So it's the addition to both of them. Okay, so if I go ahead now, just to simplify our analysis, not to have to carry this all the way along, let's go ahead and call this Q4A. We don't have to do that, but it just simplifies it. So we know, so Q flow plus source. And we learned in the previous lectures that source of uniform flow going only in the x direction is equal to this, minus Q4 pi r, this is a source, plus constant. And as we move forward, you're going to see I'm going to carry my A, because what I'm going to do is, just to simplicity, to simplify my analysis, I'm going to call it A over R, but remember, A is nothing but Q over, and a constant, Q over 4 times pi. Okay? So now that we have that, what you can do is, since this constant can take any value, it's a constant. So the best way and the wisest way to do this problem is to say, you know what, I'm just going to take this constant equal to 0. It's a constant, it's a number. We will set that to 0, and that satisfies our solution, and it's convenient. So in our particular problem, what you will have is, in such a case, remember, is partial of phi respect to r, will u infinite cosine of theta plus ar squared, and then u theta will be 1 over r partial of this respect to theta will be minus cosine of theta. And then u phi is equal to 1 over r sine of theta partial of phi respect to phi, and that's equal to 0. Okay, it's not a function of phi at all. So now we have our velocities, and now let's see if we can understand the problem itself. Okay, so in the problem, when I'm doing this problem, what you have to understand is, first of all, this is the stagnation point. Okay, this location right here, you're going to find that your UR has to be 0. Okay? And this is equal to pi. So let's say your UR was equal to this expression. Okay? And you can see that in a stream right here, when cosine is equal to pi, this is equal to minus, but this term has to be 0. We know that, right? So keep that in mind. So an RS is the distance from your stagnation point to the location of your source. Okay, remember your source is going in this direction and generating flow in this direction, this direction, this direction, this direction. So now when we move on, let's go ahead and do some math here. So we know that theta is equal to pi and 0. Okay, so this is for stagnation point. At this stagnation, so that means at this location u theta is equal to 0. Let's make sure that is true. So u theta, when it's equal to 0 and pi, this has to be 0. Okay. Well, actually, let me take that back. This will be 0 because there's no flow across the axis. Okay, we are strictly here. There's no flow that goes in the theta axis. Okay, we are just staying right here in this axis right here. So if you think about it, this is UR, right? Unless I have an influence of theta, then that's the only possible way I can have that value. Okay, so let's see what happens when pi is equal, theta is equal to pi. Why pi? 0 is in this direction, but my stagnation point is on this side, okay? So therefore, this is going to be minus pi. So minus pi from the location of my source, okay, is from this side. You can see I'm on this side. This is pi. If I was on this side, it will be 0. So your UR has to be 0. So U infinite cosine of pi plus AR squared has to be 0. And this is minus 1. So from here, this problem we find that A squared is equal to B infinite. And then from here, you can solve for your R. And your R is equal to nothing else than your RS. That would be the RS that we are looking for, A over B infinite. But remember, what was your A? A was the strength of the source, pi B infinite. Okay? So that's this distance right here, RS. That's the distance that we were actually looking for to understand what was it. Okay, so now let's see what's the point tangent to the source. So to understand this, I am just going to simplify our analysis here a little bit. So in this particular problem, this is the stream, if you would. This is not the potential. This is the stream now. Okay, and the streams are perpendicular to the potential. Remember that always. So this is 90 degrees to phi. If you remember, we had your potential like this, right? And then you had your size in this direction. Okay, so that's just basically how we derive this. So if I want the tangent to the point of my source, then I can do the same thing, and I find that this is equal to this. Okay, so now at stagnation point, again, at stagnation, theta is equal to pi. Okay, so psi at pi would be it gives you minus 1 plus constant is equal to 0. So you find that A is actually equal to the minus constant. Okay, so in other words, then your stream becomes u infinite r squared over 2 sine of theta squared minus sine squared of sine theta squared a cosine of theta minus a. Okay, so by doing so, what we really have, we have found the following values, and this is important, and this is what really at the end of the day, uh, sorry. So at the end of the day, this is what you have. So this is the stream. Okay, just tells you what the stream looks like. It's not the potential flow, it's the stream. Okay, so if you have your R equal to this value, then we have found that RT is equal to your RT, tangential value of your RT at this point, that radius that you go from there, from here to the tangential point of interest, that will be the R that you're actually going to get your point. Okay? So if we had that, we can do some more math here. We can go to your equation. Just remember your psi was equal to v infinite r squared sine of theta squared minus a 1 plus cosine of theta. Okay, I could express it like this. So at pi, we know that the stream has to be 0, so this has to be completely 0 here. Since it has to be 0, a 0 on the body surface, then I can replace that pi over 2 all over the place. Why? Because I want this location, and this location right here is pi over 2. This location here is pi. Okay, so if I put a pi there, I find the first equation. This has to be 0. Pi over 2, sorry. Um, and pi, this is satisfied, because if you realize at pi, sine at pi is 0, and this term becomes 1 minus 1, that also gives us 0, so this is immediately satisfied. Pi over 2, however, does give me some interesting results, and just remember, this is the expression that we have, but don't forget what is your u. Your a was q over 4 pi, okay? But also remember, this was rs that we already defined it, so that means your tangential radius would be square root of 2 times rs. Okay, so now we have the distance rs, we have the distance rt. Okay, all those concepts are important as we move forward. So now, the maximum radius of your body. What is going to be maximum radius of your body? Think about, this is your maximum radius, is right here. Okay, so you cannot have nothing more than this. But from your source, you know that the maximum distance would be anything that can go from here to wherever I want to locate this, right? So there's a location from here to the source to wherever I want it. That is my R. Okay, so the question is, how big does the body get? Okay, so to understand that, let's understand a couple of things. So first of all, what happens when I go downstream? Okay, so my psi, again, my psi, remember, my psi was equal to u infinite r squared over 2 sine of theta squared minus a 1 plus cosine of theta. Now, if I want to see how far can this go in this direction, that is 0 angle, right? So if I put theta equal to 0 now here, look what happens to the body. So I know that has to be, so this psi gives me 0. This goes away. I get minus. Um, so let me explain this. So when this goes to infinite, in the infinite stream, right? So now you're trying to go to 0, right? When you go to 0, you're going to infinite. What happens in infinite? Infinite, you still have your velocity, your vector, right? Your uniform u infinite that goes in that direction. So your cosine sine doesn't play much of a role there. And so you have this is equal to divided by 2 minus a2. So when you want this to really to be 0 on this line as well, so if you want that to be 0, then you can show that your a is actually going to equal to uh, 4a u infinite squared, uh, sorry, your r. And then this is nothing else than 2 times your R L is going to be 2 times RS. This is the maximum R you can have in the body uh, for the source. Okay, so now let's go and see the velocity on the infinite body that you're working on. Okay, so we found the constants, we found everything. So let's just go ahead and replace all the values in here. Where you have basically UR is equal to this value, UR is, then you replace the value for A that we just found, gives you this. U theta is equal to sine of theta minus sine of theta. Then if I have that value, now what I could do is, and I want to find what is my total velocity. Your velocity is nothing else than v squared is equal to ur squared plus u theta squared. Okay, so if I square this whole thing, you can show that what you're going to get is the following: infinite squared 1 plus RL squared over 2 times R squared cosine of theta plus RL squared 16 R squared. Okay, this is RL. Okay, okay, this is the total velocity that you're going to have. So now we can go ahead and we can also say that on the body surface, your psi is going to be 0. Remember, your psi is 0 everywhere here and on the body. Okay, your stream, there's no velocity here at the body. Okay, so your stream function. So we know that's the 0. And that was equal to r squared over 2 a 1 plus cosine theta. Remember, we are working at, as I go to theta approaches 0, right? Go to infinite on my right-hand side. So that's why this term is not there. So you have from here that your R body will be nothing else than, you can solve for this and set that to 0. That would give you, R body would be 2R 2RL squared u infinite divided by 4, 1 plus cosine of theta divided by u infinite. Okay? So, given that, now we can go ahead and do some simplifications. We find that our body is actually the same thing as RL, 1 plus cosine of theta divided by 2, or Using trigonometry, you can show that this actually gives you cosine theta over 2. Um, your R is nothing else than RL squared cosine squared theta over 2. And if I'm going to take the ratio of what is your RL squared divided by my total R, then you can show that this is equal to 4. And so you can at least understand where this comes from. R squared divided by cosine theta over 2. Um, all of this divided by R squared sine of theta squared. And then if you do some mathematics here, you can show that the answer you get is 1 minus uh, R over RL squared. Okay, so that's ratio squared, that ratio that you get there. So basically what we have said now is that your R squared that is equal to RL squared over 2, 1 plus cosine of theta, and uh, R body has to be less or equal than RL. Okay. Um, I know this is a lot to digest right now, but we're going to do an example and everything will be a lot more clear, hopefully. Um, so we move on and we want to know what's the velocity on the surface. So the body surface velocity, okay, squared would be u r squared plus u theta squared. And we already showed you this. So we have been doing all this so we can replace these values in here plus RL squared 2 times R squared. Now I have this expression. I know what it looks like. I know what cosine of theta looks like. I know what R, capital R, sorry, to the fourth, 16R to the fourth. And if I replace all this value in here, then your surface velocity is what I was really going after, is actually equal to 4 times R over RL squared minus 3 times R over RL to the fourth. Okay, you can do some math. You can show that's the answer you get. Okay, so we're almost there now. And so let me go ahead and show you what we have so far. So this is what you really have now. We have found all the radiuses. How much is maximum radius is 2 times s. Your s is this distance here. So what we have done is we have said this heat sink, right? If I have the heat sink, we're going to have a flow. If this is generating a source, so you got a flow that's coming in this direction, and they're intercepting each other, right? They're seeing each other, and that's going to create a nice line here, and that line actually looks like this. So that's basically what we are trying to do here. And we found now all the dimensions. We know what the velocity looks like as well on top of this. Now, I have all this information. The big question that I started all this with, I got this body sink, I got the source, sorry, and I want to know in the source, what is my drag? Okay, at the end of the day, this was the whole purpose of this exercise. I told you that somehow all of this is related to finding one of the aerodynamic quantities. So if I wanted to find the drag on the body surface, it will be done as follows. We go back to Bernoulli because Bernoulli helps us understand, gives us some interesting information that we need. Okay, so we know this is P infinite over rho plus V infinite over 2. So in other words, what we can show from here, I can solve for P. Or just go ahead and say P is equal to P infinite squared. I'm sorry, plus 1/2 rho V squared 1 minus V over V infinite squared. And if we realize this quantity we found, right? We know that quantity. It's right here. Okay? So I could, this V divided by V infinite, I can replace it there. And then you can show that your PR, everything in a function of R, would be the following equation. Rho infinite 1 minus 4 times R over RL squared plus 3 R RL to the fourth. And there's a purpose why I wanted to find this. Remember, I do this because at the end of the day, what you're going to do is you're going to want to equate the this is going to give you the pressure acting on the surface gives you what the force is acting on the surface, right? So to understand what's going on here, um, you have the velocity, and then I'm going to take, you got the source, and the source is generating this nice Rankine body. And then I want to see is this is going in this direction. I'm going to take a small strip. This strip looks like this. This is the component I care for. I'm not looking for the lift right now. I'm just looking for the drag. It's this component right here. So that's this component. This is my pressure. You can see the pressure is coming here, and then that pressure is generating a drag component that will be in this direction. And that is the component that I really care for. Okay, so with that said, um, the pressure normal to the surface, okay, so let me write this down. The normal pressure load on the strip will be 2 pi r, okay, ds. This is the total area. This is the strip area times your pressure, okay? Then the component of your pressure, component of your drag, sorry, in the x direction will be 2 pi r ds p cosine of theta. Or basically, if I replace all the values here, then you can find, you can just show that pi is actually equal to p 2 pi r dr. And how do I show this? Well, you can do this because you can easily show that you can find this in trigonometry function. So you can separate this. This is your dr. This is your total ds in this location. This is theta. You can do your angles and you can solve for that. Okay. So then this is what I would say my my drag acting on the strip. So my total drag then will be r equal to 0 going from the center, going to r equal to maximum, okay, maximum drag I can have. So this will be p 2 pi r dr, or this is going to equal to 2 pi r equal to 0, r equal to r PR R dr, where your PR is nothing else than this expression that we have here. So you plug in all this expression there, and that will actually give you the value that you're looking for your drag in a Rankine body. So this concludes we did all this just to find the drag in a Rankine body that has a source on the inside.